Assignment 1.b, C, making the layout of CMOS 2 input NAND gate and CMOS 2 input AND gate and verifying its functionality. Referring to the schematic in front of us, we see for the layout of a 2 input NAND gate, we have two PMOS transistors P1 and P2 connected in parallel and two NMOS transistors N1 and N2 connected in series. The source terminals of P1 and P2 are connected together using metal 1. Similarly, drain of P1 and P2 connected together using metal 1, and this connection is defined as output node. Also, we see that the drain of N1 connected to the intersection of the drains of P1 and P2. Similarly, source of N1 connected to drain of N1, while the source of N2 is connected to ground or minus VSS. Also, the gate of P1 is connected to gate of N1, and to this intersection we are applying the input A of the NAND gate at a frequency FA. Also, the gate of P2 and gate of N2 are connected together, and to this interconnection we are applying the signal B at frequency FB. It is important to note that the frequency of signal B, FB, is twice that of the frequency of signal A, that is FA. Now, P1, P2, N1 and N2 form the transistor level schematic for a 2 input NAND gate, and in order to obtain the functionality of an AND gate, we connect the output of NAND gate to the input of a CMOS inverter, which is formed by the transistors P3 and N3. So P3 and N3 are connected as the conventional CMOS inverter, and in order to connect the output of NAND gate, that is Y NAND, which is available at metal 1 layer, to the input of the CMOS inverter formed by P3 and N3, which is available at polysilicon layer, we have to use a metal 1 to polysilicon contact, which is indicated with a pink colored crossed square. So using this contact, we are going to connect the output of NAND gate available at metal 1 layer to the input of inverter available at polysilicon layer, and the output of CMOS inverter formed by P3, N3 is now the output of the AND gate. Now we go to the layout and try to convert this transistor level schematic into the layout of both NAND and AND gates. Remember, we have to use 90 nanometer technology for making the layout. So we will first place all the MOSFETs as per the schematic here. So we will place P1, P2, P3, N1, N2 and N3 in the workspace. MOS generator, PMOS, generate device. Now we can copy this transistor 2 times. We can copy this transistor once and paste it 2 times. So go to copy elements, select the PMOS and place it here. Again we can copy this and place it here. Take NMOS, place it here, copy it, place it here, copy it again and place it here. So note that this is P1, P2, N1, N2, P3 and N3. So these two devices will form the CMOS inverter, and these 4 devices will form the NAND gate. So we will place them apart so we don't get any design rule check errors. Now we will align them properly. So note now that this is P1, P2, N1, N2, P3 and N3. Source of P1, gate of P1, drain of P1. Source of P2, gate of P2, drain of P2. Drain of N1, gate of N1, source of N1, drain of N2, gate of N2, source of N2. Source of P3, gate of P3, drain of P3, drain of N3, gate of N3, source of N3. We will start making the connections now. So source of P2 will be connected to source of P1, source of P1 connected to source of P2. Similarly, drain of P1 will be connected to drain of P2. Connect the source of N1 to the drain of N2. Connect the drain of N1 to the intersection of drains of P1 and P2. Now we can connect the gate of P1 to gate of N1 by using polysilicon layer. Similarly, connect the gate of P2 to the gate of N2 in this way. Take polysilicon. We can zoom and we can delete the extra sections. Apply VDD. Apply ground. Polarize all 3 N wells. Now we can make the connections for CMOS inverter. We can align it. With polysilicon, metal 1, apply VDD, apply ground. Now we can define the intersection of the drains of P1 and P2 as the output of NAND gate. Select visible node and place it here. Name it as Y NAND. Now we can take a complex contact poly to metal 1. We can put it here, and we can connect the output of NAND gate to the input of the inverter. We can little bit move this output here, and we can take metal 1, can connect it here. We can take polysilicon, connect it here. We can actually move the inverter And we can take polysilicon, we can continue connecting it. Define the output of inverter as the output of AND gate, Y, A and D. Click AND. Now we will apply the inputs A and B. Take a clock and drop it in the intersection of the gates of P1 and N1. Name it as A. Let the frequency be 2.5 gigahertz, for which time high and time low will be 190 and 190 picoseconds. Click assign. Take another clock and drop it at the intersections of the gates of P2 and N2. Rename it as B and make it double the frequency of A. So make it faster and faster. So now signal A is at 2.5 gigahertz. Signal B is at 5 gigahertz. Click assign. Now perform a DRC. There are no design rule errors as indicated here, no design rule error. Now we can run simulation and check for the functionalities. Make sure that the visibility of output of NAND and AND gates is on. Double click Y NAND, visible in simulation. Double click AND, visible in simulation, and say simulate. We can remove all the checks and we can show more number of cycles. So we can verify it like this. So for A and B, for 0 0, output of AND gate is 0 and that of NAND gate is 1. For 0 1, output of AND gate is 0 and that of NAND gate is 1. For 1 0, output of AND gate is 0 and that of NAND gate is 1. And for 1 and 1, output of AND gate is 1 and output of NAND gate is 0. So we can clearly see that because NAND and AND gates have exactly opposite functionalities, the waveform for AND gate and NAND gates are exact complements of each other. And here rise time and fall time are not to be focused, so we are not making those measurements. Dynamic power dissipation is 17.48 microwatts and the functionalities of AND gate and NAND gate are exactly matching with the truth table of AND and NAND gate. Close this. We can save this on the desktop as CMOS NAND underscore AND. Thank you.